Welcome to this two-video series on graphing via transformations. In this first video, we'll discuss the basic rules of what a graphic transformation is, and in the second video, we'll get into more complex problems. Let's start with what we mean by graphing via transformations before we actually do any problems. The ultimate goal of this video is to teach you how to use a library of functions, more on that in a minute, to graph things like this without a calculator. Now, of course, we could graph any of these things on a graphing calculator, but the real purpose of mathematics is not the end result, but it's the mental process that we go through. So there's a tremendous value in learning how to do things without a calculator for the improvement of your brain. And this video will show you how to graph things like these functions without a calculator. So, the first skill necessary when graphing something this complicated is to recognize it for what it is at its core. What we really have here is a squaring function with some modifications, the cubing function with some modifications, and likewise an absolute value function and radical function that are slightly modified. And so the first thing that you want to do when you're graphing a function like these, the ones on the right I mean, is to recognize them for what they are at their core. And then you can use the following logic. If you memorize the graph of y equals x squared, which is one of the functions that is worth memorizing, we put it in our library of functions, the functions that we should sort of know by heart. If you know what the graph of y equals x squared looks like, then the only question is, what effect do the -2 and the -3 have on that? How does that transform into a different graph? And there's ways to do that, which is what this video will teach you. Likewise, if I've memorized what the graph of y equals x cubed looks like, then to graph the more complicated cubic, I simply have to ask myself, what effect do the -1 multiplier, the +4, and the subtracting 1 on the end have on this? And they have a transformative effect, but you're going to end up with a general cubic shape either way. Likewise, if I memorize what the graph of the absolute value looks like, then to graph the more complicated absolute value, I simply have to ask what effect do multiplying by 2 and subtracting 1 have on a function? Or if I know what the graph of radical x looks like, then I can ask what effect do adding 5 to the function and subtracting 3 from the variable have in transforming this into a new radical function? So the purpose of this video is to learn all of the transformation rules that are associated with our library of 4 functions. Now, are there other functions that you might be asked to graph someday other than the squaring, cubic, absolute value, and radical? Sure, depending on your course, you may be asked to graph exponential functions, logarithmic functions, sines, cosines, and tangents. There are many other functions in the so-called basic library of functions, but I've found that 99% of the time, questions arise among these 4 basic functions that you see in red in the middle here. So by memorizing those and learning the transformation rules, we'll be able to successfully graph any variant of these 4 functions without a calculator. So let's take a closer look at the transformation rules. First, we're going to take a look at what happens when you do an algebraic operation to the inside of a function, meaning to the input variable x. And we're going to start by looking at addition. If that seems a little vague, here's an example. Notice that here we have the squaring function, but we're adding 3 to the variable x inside of that squaring function. Here we did the same to a cubing function, or an absolute value function, or a radical function. All of these involve adding 3 to the variable on the inside or to the input of the function from our basic library. Let's take a look specifically at the squaring function in this case. So if I were to graph this thing without a calculator, I would go to my library, recall what the graph of the squaring function looks like, and then simply ask the question, what does the plus 3 do to that function? Well, it turns out, rule number 1, whenever you add a number to the input variable, you shift the graph or transform the graph that many spaces to the left. And so the graph would be here, 3 spaces to the left of the original one from my library. Something worth noting about doing graphs by hand, we could indicate that it's 3 spaces by putting in tick marks, and most teachers probably would have you do this. As a personal preference, I think the tick marks are a huge visual distraction, and I tend not to put them in myself, and I recommend you do the same. So without them, we can still indicate that the parabola has shifted 3 spaces to the left by just putting a -3 there, and that's enough information to convey that thought to the reader. Here's an afterthought, and while I'm done with the problem, why does a +3 cause a shift leftward in the graph? Shouldn't plus cause a rightward shift? Well, the reason for this is extremely interesting, extremely complicated, and kind of far off the point of this video. So for now, accept it as just a discovery that was made, and leave the reasons for it aside. Here's our second example. Notice in all these functions, we've subtracted 2 from the input variable. In other words, we've subtracted 2 inside the function. And it turns out that in all of these cases, the function from the library would be shifted 2 spaces to the right. Let's take a look at this one in particular. So if I were to graph this thing without a calculator, I would go to my library, pull up the absolute value graph, essentially from memory, and then realizing that this equation has a -2 subtracted from the input variable, and knowing that that always causes a translation or a shift to the right, then my new transform graph is going to be 2 spaces to the right of that. And of course, the same logical question comes up. Why does subtraction by 2 cause a shift to the right? Intuition would tell us that subtraction by 2 would cause a shift to the left. But this is sort of a counterintuitive to the science reality of the situation. And again, I will leave the why or the reasoning for that for another time. Let's take a look at a third example here, where instead of adding or subtracting to the input variable, notice in all of these cases, we're multiplying the input variable by -1. A -1 turns out to be a very special number in mathematics, and we call it a negation when we're multiplying something by -1. It turns out that, and we'll look particularly at the radical graph here, but it turns out that multiplication by -1 causes a horizontal reflection. I'll show you what that means. Here I would go to my library, pull up from memory the radical graph, and then because I'm multiplying by -1, I would reflect that through the y-axis. That's another way of saying a horizontal reflection or horizontal mirror image. And that will give me this as my graph. And while I am done with this problem, there's the answer in green. There's something worth noting here as an afterthought. And this has nothing to do with transformations specifically, but let's talk briefly, before we go on to our examples 4 through 10, let's talk briefly about what it is that a graph means. We don't want to lose track of our basic fundamentals just because we're learning a new set of rules. So we've just graphed
y equals radical negative 1 times x, supposedly, according to these transformation rules. And it is correct. But let's think back to what a graph actually means. A graph is a collection of xy pairs that make an equation true. So shouldn't I be able to pick any random number for x, plug it in, get a y value, and thereby discover a point on this graph? So we'll do that. What if we were to say, let x be negative 4? Just as an example, there's nothing special about that particular number. If I were to plug negative 4 into the function, watch what happens when I work it out. I get a y value of 2. Well, if you think back at what graphing actually means, doesn't that mean that this function should contain the point negative 4, 2? After all, we plugged in negative 4, and we got a result of 2. Well, it turns out it does. Watch the graph and you'll see. If we were to go 4 spaces to the left, or an x value of negative 4, and up to the graph and find that point, it turns out that that point does in fact have a y value of 2. I'm not suggesting when you're graphing by transformations that you should plug in random points. This is not a how-to moment in this video. What I am saying is that with all the tricks we're learning here about graphic transformations and the use of the library of functions, you should, at the end of the day, produce a graph that physically represents the x and y pairs that make that equation true in the first place. Otherwise, it's meaningless. Before we move on to our fourth example, let's look at one more point here. If you were given this problem in most venues, you would not see the time sign. In fact, quite often, you wouldn't even see the 1. And you should recognize these 3 algebraic forms as equivalent just from your basic knowledge of algebra. So be on the lookout. You won't always see the time sign, and you won't always see the 1. But even if you don't, such as in the bottom line here on your screen, you are still multiplying by negative 1, whether you see the 1 or the multiplication sign or not. So now let's look at our fourth example on what happens if we multiply the input variable by a number greater than 1. Here's some examples. Notice in all 4 of these cases, we're multiplying the input variable x by a number greater than 1. Now for convenience, I chose the number 2, which is of course greater than 1, but this would work for any number greater than 1, not just the example of 2. Okay. In particular, let's take a look at the squaring function when we've doubled the input variable. So to graph this, I would go to my library, pull out from memory what the squaring function looks like, and then because I'm multiplying the input variable, or the x, by 2, that's going to compress horizontally by a factor of 2. What that ends up looking like graphically is this, and you can see that the red or original library function got compressed into the green one, which is the answer to this problem. And while I am done with the problem, let's say a little bit more here. What does it mean to compress horizontally by a factor of 2? That's a strange sentence. Watch the graph and you'll see what that means. It means if we were to have any random point on this function, the original one from the library, and suppose that point were some distance away from the y-axis. I just made up the number 2.6. There's nothing special about that. But if we were to take a point that was a certain distance away from the y-axis, there would be a corresponding point on the transformed function. And because it's compressed by a factor of 2, that means that that distance would be half of the original distance away from the y-axis, which in this case would be 1.3, half of 2.6. Here's another example. If we had some random point that was any distance away from the y-axis, suppose it were 2 spaces away, there would be a corresponding point on the transformed function, or the new function. Because we're compressing by a factor of 2, that point would be half the distance or one space away from the y-axis. So in a compression like this, everything essentially goes half the distance to the y-axis. Let's take a look at our fifth example. Again, we're going to look at what happens when you multiply the input variable x by a number, but this time we're going to look at a number less than 1. A half, of course, is less than 1. There's nothing special about a half. I just chose it for simplicity. This technique you're about to learn would work for any number less than 1. Let's look in particular at the cubic, where we've multiplied the input variable by a half. So to graph this without a calculator, I would go to my library, take from memory what the cubic function looks like, and then because I'm multiplying the input variable by a half, I would stretch it horizontally by a factor of 2. If you're wondering why multiplying by a number less than 1 causes a stretching, if that seems counterintuitive to you, it is counterintuitive, but it is the scientific reality of these graphs. So the ultimate graph would look like this, as you see here in the coordinate axes. And while I'm done with the problem, let's talk a little bit briefly about what does it mean to stretch horizontally by a factor of 2. What that means is if you were to take any point on that graph, say some random point that was a certain distance from the y-axis, 0.8 spaces, let's say, that there would be some new point on the transformed graph that was double that distance away from the x-axis, the y-axis. In this case, that would mean it would be double of 0.8, in other words, 1.6 spaces away from the y-axis. Similarly, if we pick some random point to the left of the y-axis, say it was 1.5 spaces away from the y-axis, there would be a point on the transformed graph corresponding to that would be double that distance from the y-axis. Doubling 1.5 would be 3. And that's what's meant by a stretching horizontally by a factor of 2. Now, up until this point, you'll notice, or you may recall, that we looked at all the possible things that we could do to the inside or the input variable of a function and looked at all the transformations that would occur under that situation. We've done 5 out of our 10 problems here. Let's now transition and look at what would happen if we do these same operations of addition, subtraction, multiplication, and so forth to the outside of the function. I'll show you what I mean by that, starting with addition. Take a look at these 4 examples. You'll notice I've added 4 to each of these library functions, so to speak, but I haven't added 4 to the variable. I've added 4 outside of the function, whether it be the squaring function, cubing, the absolute value, or the radical. The addition of 4 is being done to the function, or also said outside the function. Let's look in particular at this one. It turns out this kind of addition causes a translation or a shift in the upward direction. So to graph this, I would go to my library of functions, take out the basic squaring function, and then because of my plus 4, I would shift that up 4 spaces, and that would be it. So, while I'm done with that problem, I want to talk a little bit more about the equation. This equation that you see here, the one we just graphed, isn't it algebraically equivalent to this? In other words, the parentheses have no impact on the meaning or the algebraic significance of this. Don't expect to see the parentheses there in most cases. Some students get confused when they see the bottom line on your screen here because they think, how am I to know if the plus 4 is, quote, inside or, quote, outside of the function? Well, it's clearly outside of the squaring function, and you shouldn't need parentheses around the x to show you that. Let's take a look at our 7th example. Notice in all of these cases, we've taken a function from our basic library and subtracted one. Notice that all these subtractions are outside of the function from our library. When that happens, you end up with a translation or a shift downward by that many spaces. Let's look in particular at x cubed minus 1. I would go to my library, take x cubed from memory, and because I have a minus 1, I would shift it down one space, and that would be my graph right there. Let's take a look at our 8th problem, this time involving negation. Notice in all these functions, I've taken the basic 4 functions from the predominant part of our library of functions, and I've multiplied all of them by -1, otherwise known as a negation of the function. Let's take a look in particular at this one. To graph this, I would go to my library, get this from memory, and because I had a -1 multiplied by the function, or outside the function, I would reflect it through the x-axis, also known as a vertical reflection, and that will give me this. Now I'm done with this problem. However, I think this would be another good moment to pause and think about, even though we're learning a bunch of transformation rules, you can learn them and apply them to all the functions in the library, I don't think we should ever lose track of what it means to graph something. So let's take a brief interlude and remind ourselves what that means. We just supposedly graphed y equals -1 times the absolute value of x. That's the graph at the bottom that you see in green. But remember, graphs represent true points in an equation. In other words, graphs represent pairs of numbers, x and y, which when plugged into an equation, make a true statement. So shouldn't I be able to pick some random x value, nothing special about -3 here, but shouldn't I be able to pick some random x value, plug it into the equation, work it out, and thereby get a point that my function contains or that is on my graph? Of course it does. Let's see what happens here. The absolute value of -3 is +3, as you'll recall from basic algebra. And when we work this out, we get a y value of -3. So what just happened? I plugged in a random x value, -3, and got out a y value corresponding to it, -3. Shouldn't that mean that my function contains -3, -3? Well, of course, and in fact it does. Watch the graph. If I were to go left 3 spaces, the function would be below, as it turns out at some point that is also 3 spaces away from the x-axis. In other words, this graph really does pass through the point -3, -3. Am I suggesting that when graphing via transformations, that you stop and plot points? No, it's a waste of time. But the purpose of this brief discussion is to remind you that even though we're learning a bunch of graphing tricks, they're producing graphs that actually make true points for the equation, which is what a graph is supposed to do in the first place. Now, before we move on to example 9, I'd like to say a little bit more about the equation itself. Notice the equation on your screen, it's the one we just graphed. Be prepared to be in a situation where the times sign is not written, and also be prepared to find situations where the 1 isn't written. You should be familiar with the concept that multiplying by -1 oftentimes excludes the writing of the time sign, and it excludes the writing of the 1. In other words, all 3 of these equations are the same. So if you memorize that, for example, multiplication by -1 outside of a function causes a vertical reflection, that's great. But if you're given the bottom equation here, you should still recognize that that is in fact a multiplication by -1. Now let's take a look at problem 9. What happens when we multiply a function by a number greater than 1? Now there's nothing special about 2 here, I just chose it because it's greater than 1. But notice I've doubled all of these functions, or multiplied the outside by 2. Let's take a look in particular at this one. If we know the absolute value graph looks like this, and we're being asked to graph 2 times that, then we should stretch that vertically by a factor of 2. That's just one of the rules, as you see above. Well, it turns out the graph's going to look like this. But what does it mean to stretch vertically by a factor of 2? That's a strange way to say something. I'll show you on the graph what that means. Suppose you had some random point on the graph. And suppose that that point were 3 spaces away from the x-axis. Because we're stretching by a factor of 2, there'll be some corresponding point on the transformed graph, and that point will be twice as far from the x-axis. In this case, 6 spaces away. And that happens for every point on the graph. Here's another brief example. Suppose we had a point that was a small amount above the x-axis. There would be a corresponding point on the transformation that was twice that distance from the x-axis. And that's what we mean by a stretch vertically by a factor of 2. And now let's take a look at our last problem. What happens when we multiply a function by a number that's less than 1? Again, there's nothing special about a half here, just some arbitrary number I chose, less than 1. Let's look in particular at this one. Here's what my radical graph looks like. Because I'm multiplying the radical graph by a half, or the half is outside the function as a multiplier, I'm going to have a vertical compression by a factor of 2. What does that mean? Well, it means it's going to look like that, compressed vertically. To be more specific, imagine we had any point on the original graph from our library. And suppose that that point were, say, 3 spaces away from the x-axis. Because we're doing a vertical compression, there would be a new point on the transformed graph that was exactly half that distance from the x-axis, which in this case would be 1.5 spaces. That's the general idea of what we mean to compress horizontally by a factor of 2. Now I'm done with the 10 examples, but let's summarize the basic properties we learned in this video. The first 5 problems included operations to the input variable, or what we call inside operations, on the function. We learned that if you add, such as in this example, you shift left. If you subtract, such as in this example, you shift right. When you negate, such as in this example that we saw, you reflect across the y-axis, in other words, you reflect horizontally. When you multiply the inside by a number bigger than 1 or less than 1, you will either compress or expand horizontally on that function. Problems 6 through 10 looked at the operations performed on the outside of a function, and we looked at an addition, such as in this case. That was an upward shift. A subtraction from the outside of a function would be a downward shift. Negation of a function would be a reflection through the x-axis, or a vertical reflection. Multiplying by a number greater than 1 would be a vertical stretch, and multiplying by a number less than 1, such as in this case, would be a vertical compression. And that completes the first video of 2 in this series.